In section 8.1, we're going to be discussing single-stage experiments. An experiment is an activity, whether you're spinning a spinner, rolling a die, flipping a coin. An experiment is the activity or the process of the activity that you do. The outcome is the result. So if I spin a spinner, I might land on the number 8, or I might land on the number 4. Those would be outcomes. It would be the result of actually doing the experiment. The sample space is a set of all outcomes. So if I have a spinner, and on the spinner I have the numbers 1, 2, 3, 4, then the sample space is the set 1, 2, 3, 4. The experiment would be the process of spinning a spinner and landing on one of those numbers. The outcome, I could either land on a 1, or I could land on a 2, a 3, or a 4. So the three terms are important for this first section. There are two methods of determining probability. One is the experimental method, and that would be by actually spinning a spinner and seeing how many times I land on a particular number. So if I spin the spinner 4 times and I land on 1, 2, 2, and 3 out of those 4 times, then that would be an experiment. It would be experimental probability. Theoretical probability is looking at the situation. I have 4 numbers that share an equal amount of area. So when I spin the spinner, I should have an equal likely probability of landing on any one number. So the probability of landing on a 1, which should be the same as on a 2, should be the same on a 3, and should be the same on a 4. That's theoretically. If I actually do the spinning, it might not be that way. So experimental is actually doing the experiment, or actually doing the activity and seeing how the numbers land. And theoretical is where you write down what should be based on what's given. The probability of an equally likely outcome, like this example, is 1 over n, where n is the number of outcomes that you could have. So we could have 4 different outcomes, and each one has the probability or is equally likely to occur. So the way I write that would be, I would say the probability of spinning a spinner and landing on a 1 would be 1 out of 4. Now if I want the probability of landing on a 2 or a 4, then half of the area of this is taken up by a 2 and the 4. So the probability would be 1/2. So experimental and theoretical. On page 523 in your book, you have the sample space for what could happen if you roll 2 die. And I think that you will find that to be very helpful as you are answering problems in your assignment, because if it asks what is the probability of rolling 2 die and getting a sum of 7, then you will be able to go back and look at these and find the numbers that would give you 7. So if the first is a 1 and the second a 6, if the first is the 2 and the second a 5, if the first is 3 and the second 4, if the first is 4 and the second 3, if the first is 5 and the second 2, and the first is 6 and the second 1, then you would all have 7. Now, there are 36 numbers that, or 36 possible outcomes. And so 1, 2, 3, 4, 5, 6 of those would give you a 7, and reduce that, and the probability would be 1/6 that you would get a sum of 7. If you were asked what is the probability that you would get a sum less than 7, then again it's just simply counting. Your denominator will always be 36 if you're rolling 2 die. And so it's a matter of just adding up all the sums and seeing how many of them have a sum less than 7. For example, a 1, 1 would, and a 1, 2, and a 1, 3. So it's just listing them and counting the number that meet that criteria. So the probability of any event is the number of favorable outcomes over the number of outcomes in the sample space. So there are 36 different outcomes in the roll of 2 die, and then you have to count how many of them are favorable depending on the conditions that are set in the problem. Sometimes you are asked to list the sample space. The textbook gives you what would happen if you're dealing with dice 2. But it doesn't always give you the sample space for everything, so you're going to have to list the sample space as they have on page 523 for different problems. One that you might have to list the sample space for would be the toss of 3 coins. Well, you know that for 1 coin there are 2 outcomes, heads or tails. And you're dealing with 3 coins, so that's 2 to the 3rd power, or 8. So there's going to be 8 outcomes. Just like on the die, there are 6 possible numbers, and if we deal with 2 die, it would be 6 to the 2nd power and 36 possible outcomes. So you can see why we don't use 3 dice, because 6 to the 3rd power is 216. So there's a whole lot of outcomes to have to deal with. Now if we toss 4 coins, that's going to be 2 to the 4th power, or 16 possible outcomes. So that could be done, but it still gets to be a little bit cumbersome. So we're dealing now with just 3 coins tossing 3 coins, and we have 8 outcomes that we have to find. So it's helpful to know how many outcomes that you're going to be looking for when you toss the coin. So I need to set up a system when I list these. So I'm going to say, if I let the first coin be tails, then the second coin could be tails, and the third coin could be tails. If the first coin is tails, the second coin could be heads, and the third coin could be tails. So I'm keeping the first and the last the same and only changing the middle. Then I'm going to keep the first and the second the same and only change the last. So that gets me the combinations that could occur if the first coin is tails. If the first coin is tails, and I keep the second coin the same, and I change the last. Now, are there any other combinations that could occur with the first coin as tails? So I'm trying to come up with a pattern that I can use when I'm listing outcomes. Alright, so that gets 4. I'm halfway there. So let's change the first coin to be heads, but leave these two the same. And I'm changing the first coin to be heads and leaving these two the same. And the first coin to be heads and these two the same. And I now have all 8 outcomes. So this is the sample space. And it's a set. So if I list the set of sample space, I use set braces. And write them out. Separating with commas. Making sure there are 8. So that's the set of the sample space. Now, if I want to find the probability of getting 2 heads, then I simply go through and look at all the outcomes. Here's one that has 2 heads. Here's one that has 2 heads. Here's one that has 2 heads. And here is one that has 2 heads. Now, you have to be careful. If it says exactly 2 heads, then this with 3 would not work. But if it just says the probability of 2 heads, well, the one that has 3, well, it does have 2. But it doesn't have exactly 2. So we have to kind of watch the terminology. So here's 1, 2, 3, 4. So 4 out of 8. So the probability of getting 2 heads would be 4 out of 8. And that reduces to 1/2. Okay, what about, okay, so let me go back now and let's look at the terminology here. If we say exactly 2 heads, there would only be 3 out of 8. If we say at least 2 heads, there are 4 out of 8. So this we will count as exactly, and this we will count the 3 heads in a row. Now, if you have the probability at most 2 heads, is that any different than at least 2 heads and at most 2 heads? In this particular example, it would not. Now, in some, it might. So you'll have to watch the phrasing of exactly 2 heads and at least and at most. If you have events that are impossible, the probability is 0. So out of that toss of 2 coins, the probability of getting a 4 would be 0. Or the probability in tossing 2 coins of getting a tails, 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 tails would be 0 because you only have 2 coins. So the sample space would be 2 events. If you are sure that it will happen, then the probability is 1. So we're going to write a statement that says the probability of an event will be 0 to 1 always. So if you do an experiment and you're ending up with a probability greater than 1, then you're doing something wrong. So you know to go back and check your math. Now if you look on page 525 at example F, you have a spinner. And the probability for each of these is based on the area of the circle that it takes up. So the orange takes up 1/3 of the circle. And the blue takes up 1/6. So does the yellow and the red. And then the green and the purple take up 1/12. Now, the probability of spinning the spinner and landing on green, red, purple, orange, red, or yellow is 1, because that's all there is. So you would have the probability is 1. You would land on one of those. Now we can combine colors And to find the probability of the combined colors, we would simply add the two areas together. So the probability of landing on red or yellow would mean that how much space does red and yellow take up in terms of the whole circle, and it would take up a third. So the probability of getting a red or a yellow would be 1/3. Or if I wanted the probability of orange or blue, that takes up half the circle. So the probability would be 1/2. Now, some terms that we need to talk about now are a compound event is could be a union where you combine them together, like I was doing with the colors, combining the blue and the orange. That would be a union. An intersection would be what do they have in common? So where is the overlapping part? Now, in the example that we just looked at, there is no overlapping part. So there is no intersection. We can combine the different areas, but there is no common area to two different colors. And then the complement means that it is not a member of that particular set, but it is a member of the sample space. So let me show you some examples of that. And this is at the top of page 526, and it's nice to look at it in terms of a Venn diagram. So if I have a set E that has red, blue, and yellow, and I have a set T that has purple, orange, and yellow, set E and T share a common color. So this would be the intersection. Yellow would be the intersection. Now the complement of T would be all the colors not in T, which is red, blue, and green. And the complement of E would be all colors not in E, which would be orange, purple, and green. Now the union would be all colors. All colors, red, blue, yellow, orange, purple, green. That's the union. The intersection is yellow. And the complement is whatever is not a member of that set. Now, if we have two sets that have no common elements, they're called mutually exclusive, and they are disjoint. So E and T are not mutually exclusive because they share a common yellow. So mutually exclusive have no common intersection, no common elements. And we write that empty set symbol with the Greek symbol. This means empty set. Sometimes we can write the empty set with empty braces. But if you put something in there, then it is no longer the empty set. So if you do this, you have a set with the Greek letter in it. So the empty set is empty braces or the Greek symbol. And that's when the two sets have no common elements and they are disjoint. So when we are trying to combine the probability of two events occurring, if the two sets have common elements, you have to take that away. You cannot count it twice. For example, when we have E is equal to the set of red, blue, and yellow, and we have T that is equal to the set yellow, orange, and purple. Yikes, purple. They are not mutually exclusive because they both contain yellow. So if I want to find the probability of A and B, I would take the probability of E added to the probability of T. Now, if they have an overlapping value, then that's when you end up with values greater than 1. And you know then that you have some common that has to be taken away. So you can't count yellow twice. Therefore, you have to take the intersection away. Now, if the events are mutually exclusive, you don't have to worry about them having something common, and you can just add those together. So if I'm looking at the probability of drawing a dime out of a group of dimes and a penny out of a group of pennies, dimes and pennies are mutually exclusive. So the probability of drawing a dime added to the probability of drawing a penny can be just added together. So you would not have any common elements in that set. The word odds is used often in racing or gambling, and it's very, very misused in the way that we speak about it. So if we are looking at the odds of an event occurring to be 4 to 3, we can write it using the colon. We can use the word to. But odds means that you're really dealing with the numerators of an event in probability. So odds, if you add them together, you get your denominator. And the numerators are here. So this is the probability. 4/7 and 3/7 is the probability for an odds of 4 to 3. So you have to be careful not to use the word odds when it's in a probability format. So they're cousins of each other. but a lot of times mispronounced, I guess. So in racing, if you have the odds of 4-1, this means that they're going to pay you back $5 if the horse wins, because you are going to get back the dollar you paid, and then you're going to get 4. The probability of you winning is 4/5. The probability of you, no, I said that wrong. The probability of you losing is 4/5. The probability of you winning is 1/5. So the numerators are the odds, and you add these together to get the denominator. So you're going to actually get back $5, but you're only going to make 4 because you are getting back the dollar that you bet. So let's say the odds are 8-3. Then if you win, you're going to get back $11, which is the denominator of the probability. So you win $8 and you get back the 3 that you bet. So the probability is 8 out of 11 that you lose, and 3 out of 11 that you win. So that's how odds and probability are related to each other. When you do experimental probability, you need to create a table to collect your data, and you will actually perform an activity. You will toss a Coke bottle in the air to see how many times it comes down up or turned down. You will flip a coin to see how many times it is heads or tails. So you actually go through the activity where you collect the data yourself. In a simulation, and you're already familiar with a simulation from one of the lab activities we did where you use the random number table, you do not deal with the data directly, but you take a random sample of the data. For example, if I wanted to predict how long it would take me, now I'm looking at the example on page 531, example K. If I wanted to predict how long it would take me if I randomly stood on campus and I asked students their birth month, how long would it take me to get 5 people? If I chose 5 people at a time, how long it would take me to get 2 that have the same birth month? So I would stand on campus and I would ask the first 5 people that came to me, and if 2 of them had the same birth month, that would be a success. Then I would ask the next 5 people that came to me, and if 2 of them had the same birth month, that would be a success. So I'm wanting to know how many times would I expect to have to do this before I would find 2 people with the same birth month. So in a simulation, they have a spinner with the 12 months on there. And so one way to do this would be to spin the spinner 5 times and write down what you got. If 2 were the same, then that was a success. If they were not, that goes into failure. And then I spin the spinner again 5 times. And if I get 2 the same, so I need a table. In doing a simulation, we have to have some way of keeping track of what we get. So on my first try, I would have 1, 2, I'm going to spin the spinner 5 times. So I spin it the first time and write down what I get. I got month 3. I spin it again, I write down I got month 4. I spin it again, I write down I got month 6. And I keep spinning the spinner 5 times, and if I do not get 2 numbers the same, then I'm going to also have over here whether it was a success or whether it was a failure. And because I did not get 2 of the same, then that's going to classify in the failure. And so I keep doing this over and over and over until I end up with students that have the same birth month. And I see how long that it took me, and then I could then expect that to be the probability. So the number of times it takes me, let's say it takes me 10 times, then that's going to be my numerator or my denominator, and then it happened 1 out of 10 times. So I would expect then to have to do this 10 times before I finally found one. Now, another way of doing this would be to use a random number table. We did that before. And in the random number table, we would read one number. Let's see, no, there's 12 months. So we'd have to read 2 numbers at a time. They have a better random number table on page 532. So I'm looking at months of the year. Let me get this where you can see it a little bit better. So 57 is the first number, so that doesn't work. 45, 57, 24, 55, 93, 94, 90, 30, 17, 33, 46, 35, and 6. I'm finally at 6. So that's my first number that's actually a month, 06. So there's 1. And then 1, 2, that's December. Then 65, 97, 61, 86, 30, 26, and then 8. I've got that one. And then 9. Oh, sorry, you're not seeing that. My hand's in the way. And then 91 and 35. So I go down now to the second row, taking 2 numbers at a time, and I'm at 0, 1. So I have chosen 5 people. So on my first experiment, I did not get anyone that has the same birth month. So in my last column, as whether it's a success or whether that was a failure, it's going to classify in the failure list. So I start where I left off, 17, 71, 81, and 10. So I finally now on experiment 2, I have 10. That's October. 31, 84, 63, 31, 44, 99, 17, 54, 34, 71, 29, 34, and 10. Okay, so I now can stop because I have 2 people in the same birth month. So according to the simulation, I only had to do that 2 times, and one of those times was a success. So according to the simulation, I would only have to do stand on campus and interview 5, and then 5, and that last 5 should give me 2 people that have the same birth month. So you can see that depending on where you start on the random number table and depending on the method you use, whether you're spinning a spinner or using the random number table, the answers to a simulation can be different. So that is why you have to make a chart and you have to show what you're doing so that, I can read your work.